Good evening and a big welcome to the second webinar on BIM for GeoSciences hosted by GeoVita and NGI. My name is Magnus Ramon. I'm head of the Environmental Geotechnics section here at NGI, and I'll give you a short introduction for today's webinar. First, short about the two companies. GeoVita is a consultancy which started up in 1991, and they have their head office here in Oslo. There are approximately 15 employees and work with geotechnical engineering and rock mechanics on large construction and transportation projects. NGI is a private research foundation established in 1953 with head office here in Oslo and offices in Trondheim in Norway, Perth, Australia, and Houston, USA. NGI are approximately 320 employees from 40 different nations and work with both consultancy and research within the market areas of geodata and technology, geotechnics and environment, natural hazard, and offshore energy. So today's agenda. In the first approximately 15 minutes, Daniel will show you some 3D modeling of the geology. For those of you who saw the first webinar, the tools used in this presentation by Daniel is the same as Per Anders showed the last time. In the second presentation, Tom will present how you can use parametric modeling for designing rock tunnels. After that, Jessica finishes off with a presentation on the workflow from remote sensing to systematic bolting design for rock slopes. As in the last seminar, we would have loved to have an open discussion at the end, but since we are running this through the platform we are using, which does not enable the facilitation of a discussion, and since we have more than 600 persons who signed up for the webinar, we will solve the question part with the chat to the right. So if you have any questions, please post these in the chat, where you can also like questions from other persons who has written those. And then we will answer the question and post them on the landing page you all used for signing up for the event. The recording of today's webinar will be posted on NGI's YouTube channels, where you can also find the first webinar. So please feel free to watch the video there afterwards. That was all the practical information. Now over to Daniel and the first presentation.
Thank you very much. My name is Daniel Persson, and I work as a geologist for GeoVita. I will talk about dynamic 3D modeling of geology for any project using Leapfrog Works. For this talk, I chose to present the E18 West Corridor project just west of Oslo, where the stakeholder is the Norwegian Public Roads Administration. And this is the stage 1 of the project from Lysaker to Ramstadsletta. This presentation will touch on these subjects. A few words about data capture, some video example, and the geological modeling in Leapfrog Works, and some visualization. Okay, so you can divide data capture into 2 phases. 1 is the planning phase and 2 is the construction phase. In the planning phase, you gather most of the data, such as basic data, which are gathered from older projects in the area and existing models, and mapping, geophysics, and core drilling. Based on this data, you choose where to do supplementary ground investigation for the project. For example, total soundings, which can be used to create the bedrock surface. And 3D laser scanning are usually used to gather point clouds to build the topography, which is the uppermost layer in the model. All surfaces and data are loaded into Leapfrog Works and interpreted and used to create the geological model. In the construction phase, you can correct and verify the model, gather measurement while drilling data, and gather rock support data. And if necessary, you can supplement with core drillings from the tunnel phase. So this is a short video of the interdisciplinary model. Here you can see topography and buildings on top of it. The red and yellow structures is the tunnels to be excavated, and the existing yellow pipeline is in conflict with the tunnel, so it will be removed. And the red and white columns are all the total soundings done from the ground investigations, which is used to build the bedrock surface, which you can see here. And shortly you can see a construction pit on the left side, which are created as an access tunnel to the white sewage tunnel. And then as we follow along the model here, you can see all the geological structures which are modeled and how the lithologies are interpreted. And you can see how the buildings are in just on top of the tunnel and what you have to consider in soils. So the big benefit of collecting data into the geological model is that objects are dynamically linked. This means that if one object changes, all objects which are contacted to this object dynamically change. For instance, you can edit surfaces with polylines representing a lithological boundary, and this polyline is then added to the surface, and all the linked surfaces will change as a result. This results in that you always have an up-to-date model. And Leapfrog Work supports multiple options of data types, such as IFC, Land XML, and DXF. And sorting through the data, it's very easy by utilizing predefined views in the model. Drawings, as you previously printed on paper, can be saved as such views. And constructions like bridges, sheet pile walls, tunnel portals, and so on can easily be viewed together with the interpreted geological model. All sections that you make in the model can be viewed live on the screen, and they can be combined with other 3D objects like the tunnel here. This makes it easy to visualize the geology and how the tunnel interacts with it. And all the drawings are pulled directly from the model, which significantly enhances the workflow. Sections are pulled, also the drawings are dynamically linked to the objects in the model, which means that you don't need to change each drawing. So it is possible to combine different models. For example, you can combine a tunnel model and a geological model. This results in a combined model which show different lithologies and geological structures along the tunnel path. By using this method, we can try to classify the different tunnel sections at tunnel depth using the Q system and the Q method. Also, this is based on surface mapping, geophysics, and core drillings. For instance, in this project, intrusives like diabase and cyanide porphyry have lower Q values than the surrounding rock, and we can try to classify these sections. This way, you also can gather interpreted distribution of lithologies and total quantity of rock types, which can give an indication on the mass balance in the project. So I'll show a short video of modeling in Leapfrog Works. So here you can see the data. We'll pull in the topography, which is gathered from digital elevation models. And then we can drape GIS data on top of these objects. In this case, I'll drape the geological surface or the mapping for the surface, and then just edit the transparency. Here you can see the geological lithologies which are repeating, and then you can see some possible faulting. And based on this, we can make a model. So all your objects are here on the left side column. These are all GIS data pulled in through geological mapping. And then you have your points as total soundings and all the polylines, which I will use in this project to modify the geological surfaces which I create. So let's create the model. We'll call it the new geological model. And then choose the surface resolution. Let's take 10 meters and use adaptive. I already created this model, so I will hit cancel, but you should hit OK. I did this because to save some time. And here you have the model. Now you should add lithologies to the model. I already added lithologies to save some time, but this is the part where you should do that. We can view it as a block model. And now let's add the topography to it so we can get the uppermost layer in the model. And there we go. Now we have one lithology, which is unknown, with the topography as the uppermost layer. So let's create some surfaces. There are a lot of different surfaces you can use in the model. For this model, I will use erosion surfaces. So I start building the model with the oldest lithology and work my way up to the youngest. And then I add the soil layer to the last. So I'll select my GIS data, and these are the lithological boundaries on the surface. So I'll start with the oldest one, which is the lowest number. And then I work my way up. And then choose the lithologies I want to build. In this case, I want to build shale. And then it will calculate the boundary, and then we can view it on the scene. And here we have the boundary. And we can edit it with a polyline if we want to add some structural data to it. In this case, I'm using a polyline, but you can also use strike and dip measurements. So I add the polyline, which is the 4DD. And then it will recalculate the boundary. And now you can see it has a dip on it. And then I'll create a new one from erosion surface and choose the next lithology. And you create all the surfaces this way until you have all the lithological surfaces added to the model. And then you can view this one also. And here you can see that the surface is just flat. It doesn't have any structural data to it. So it obviously needs to be edited. And I will add a polyline to this surface to edit it. Based on my interpretation of the surface, it should be folded. So I'll add some folded polylines to it. And then it will recalculate the surface. Oh, that looked much better. Okay, now we can add another surface. This time we'll choose an intrusion to model a cyanide porphyry. So you choose the intrusive rock, then add it to the model. And then you have the object appearing. And then we add one more surface. This is almost the youngest one. So we have two more surfaces to add to the model. This also we need to edit with a polyline. So we add polyline to it. There, looks better. It's as a folded surface. Then we add the last lithological boundary. Okay. This should be just a small area on top, so we gotta add some polylines to this also. Okay, so it looks better, but it looks quite wide, so we gotta thin it. So we can open the surface and edit the trend. And then we can edit the ellipsoid ranges. Let's try this. Okay, that looks better. Let's add the surface. This one will add from the bedrock mesh, which is created from total soundings. And the soil is the youngest boundary in the model. Okay, so now we have all our surfaces, and now we gotta open them and activate the surfaces to build the volumes for the model. There we have the model. We can turn off the sediments. And then we have the lithological areas. And this is a faulted model, so we gotta add some faults. And I have the fault boundaries here, which we can add to the model. So I'll add all the 4 fault boundaries. And then the last one we'll add. Okay, and we can view the surfaces created for the faults. Here we have the surfaces. And up in the right corner, we gotta terminate one of the faults against the other one, and then that we can do with opening the fault systems and hit on the fault that we want to terminate and add it. It should terminate against fault 1 on the southwest side, and then okay. And then we gotta activate the faults. And now the model is created into each fault block. And we can view these blocks by dragging them to the scene. Okay, so now we have the complete model. We can turn off the sediments to look at the lithologies. That's good. That looks pretty good for a quick model. To the model, you can edit or add structural data. Let's just slice through it, and then we can scroll through the model and see how the lithologies change. That looks good. That's a quick tour of modeling. So there are many advantages by having a geological model, where some are listed here, but one of the biggest might be the possibility to visualize the interpreted data in a new interdisciplinary way. And by doing this, we might be able to optimize the tunnel path and minimize the geological risk for the stakeholders. And this might contribute to a more subtle risk assessment for all parties. Thank you. If there are questions, contact me afterwards. We will also answer submitted questions. Thank you, and now over to the next presenter, Tom Frode.
Thank you, Daniel. My name is Tom Hansen, and I'm an engineering geologist in NGI. And I will present how to use parametric modeling in rock engineering design, particularly for rock tunnels. I use examples from drilling for rock routing and rock bolting, and I will mainly use the tools from Rhino and Grasshopper. Grasshopper is a plugin in Rhino. It's a graphical programming interface. And it's the same as Java or Python or other programming languages, but this is a graphical one, and it's targeted for use in 3D modeling. So first to rock routing. In rock routing, the goal is to prevent water leakage coming into the tunnel. And to do this, actually in Scandinavia, that's a normal method to drill a lot of holes and try to hit as many joints as possible. And in these holes, we inject cement-based grout with high pressure and try to build a kind of a watertight barrier around the tunnel. But this is a rather static process in most tunnel projects today. And basically we use some kind of this geometry for all projects and you use the same in project to project and also along the tunnel, even though the rock mass is changing all the time actually. For each blasting round, the rock mass change and also the joint systems to hit with your drill holes. And the goal is to hit as many joints as possible to prevent water leakage. So we need a way to, in a quick way, change the geometry of this drilling. And to do so, we can use Grasshopper. It's a bit of a spaghetti here, but it's some structure here. This is a system where data flows from left to right, basically, in the script. If you need more information about Grasshopper, you can see at the first webinar. We have input values there, we have geometry design here, analysis and export, and down here we add some geology. And this script, creates this geometry dynamically and make it possible to communicate and visualize and play in a very quick way with the geometry. Also for all the stakeholders in the project. And we can, here we have taken in a profile from a standard railway tunnel in Norway, where you can put in every profile you want to have. And you can use all kinds of input values to quickly change this geometry. So we see here from above, quickly now, we can go and change the length of the holes, for instance, like this. Or we can play with all kinds of variables for changing the geometry. We can add change the inclination of these contour holes, the number of holes, or the face holes here. Typically, we'll have different systems of face or contour. So this makes it quick to change. We can also add some barrier holes if you want to. This could, for instance, be in zones with low overburden or very weak rock mass. So in the same way, we can add and play with this geometry for a barrier hole, which we typically will drill and grout first. And in the same way, you can change the geometry on this barrier curtain over the main curtain. Also the arc of this system. We turn it off again, and we will try to, in a way, visualize how the grouted zone is around each hole. We can, for instance, set it on 1 meter just to have a visual indication of how this will be. And the main goal here is to check that you have overlap between each hole, so we'll have a tight barrier. So we can also add some more curtains to check, especially the overlap between each of these curtains or umbrellas, we sometimes call them. Especially in complex geometry, this will be very important. We turn them off again. And then, when we are happy with the design, we can export it quickly, for example, to a CSV file or Excel file with a click of a button, and have these kinds of sheets, which can be imported in a drilling jumbo in a tunnel, for instance, in a format that's suitable for the rig or whatever you need it to. So here you have the hole number, start and stop, and length, and all coordinates. We can also bake this geometry to Rhino to make a digital model. So we bake it to Rhino, and then we have this 3D geometry, and we can export this to all kinds of typical file formats like DXF or IFC or whatever file format we need to process in all the programs, or in a federated model, for instance. So here we use DXF. Yeah, and we call it just geometry, and export it to a DXF to import. Yes, so we just remove it again. But we can do this better. This was just a manual change and adaptation of the model. We can do it better. We can try to add some geology. What's really important is to change this geometry for every rock mass section. And typically in the planning phase, we do surface mapping, also maybe some core drillings, and we can have typically plots like this with 2 joint systems here. Or in the operation phase, we do mapping on the face and in a detailed manner map the jointing systems, the width of the systems, and how many joint sets we have. So here we put this tunnel in a kind of a rock mass box, so we have a confined environment just to make it easier visually. And then we can start to add the geology we want to have. Here we just add some joint systems, some joint planes with the strike and dip we want to have. We can see how this is visually. And we can, to make it a bit more complex, we can add 1 more joint systems. And the task now will be to try to change this geometry to cope with the geology in an optimum way. You can see it here visually. I can turn on the model and have a kind of a nice visual inspection of the geometry. You can also add a dike here, or this could be a weakness zone or whatever that's important for the grouting drilling. And here we know that this could be important that all the drill holes hit this dike in the roof. So when we are happy with this design, we can change the geometry in the same way here. And we see that for this joint system, it could be smart to move the holes kind of to the right and hit more joints in that way. And so when we are happy with this, we can export it in the same way as I said before. But as humans, we are not very good actually to try to hit all these joints and find the optimal way to find that hit all this jointing system, especially in complex joint systems. And for this reason, we can then add some more complexity and let the computer do some more of this optimization process. In Grasshopper, we have a plugin called Galapagos, which is a model where you can use evolutionary optimization for geometry. So let's see how this can go. So we have the same model with the geology, and we have an optimization engine here. And first we need kind of a fitness function or a goal to optimize. And here we have calculated the joint hits, or the hits of drill holes to surfaces or joints in a model. You can see here 82 and 40, and we sum all the geology or the joint hits from geology we have in the model for a total number, and we want to maximize this number in this model. And to do so, we need to input variables to change and to make thousands or millions of combination of input variables or versions of the geometry. And here we will change the vertical direction and the horizontal direction of all holes. And also we will change the inclination of the face holes. So we have 3 variables there that can change in an interval, which we set. So then we can try to maximize this. We see 182 now. This is the Galapagos module, and we start with a population of 50 times 2 or 100 different combinations. That's where we start the evolutionary process. And we keep the best ones, and we do it like that. I will not go into detail of evolutionary optimization now, but we just start this algorithm, and we start to see that the geometry changes all the time, and the engine tries all kinds of different combinations based on the variables we have set up. And you see here in the first phase that the geometry varies a lot. It tries all different combinations, and I'm kind of not sure where to go. But with time, you will see that more and more of the holes get focused to the upper right, and the model in a way stabilize. So the evolutionary process goes in the right direction. These get kind of converging to some values here, and more stabilized with time. You can also see the joint numbers down there on the right, how it changes with different variables. So we'll let it just continue for some seconds more to see if it's kind of hit a target. And we see it's fairly stable now. So we stop it there. It's kind of maximized. We had about 220 joint hits, and we can expect the worst one with 119 joint hits. You can see it's directed down to the left, which is obviously a bad solution. And we can expect the best one with almost double in joint hits, 222, and we see this geometry on the upper right. So this will be an optimized model for this geology. And then we can export this more optimized solution to use in a drilling jumbo for this, actually this rock mass in this area, in the same manner. Okay, that was for one grouting curtain. Now we will have a look at how we can do this for a discipline model for rock grouting. So here we have a center line for a tunnel in Rhino, and we have a script that will generate this discipline model, or all the planned drill holes for this grouting, for this tunnel. We have a tunnel surface generated here. We read in some data. We place geometry, and we make a quantity report dynamically. So first we connect this center line of the tunnel to the script. We see some values loaded. And we can have a bit closer inspection of it and see the geometry. It's the same profile we used in the last design. That's the railway tunnel. You can also, for instance, change the distance between each grouting curtain. Let's say 20 meters. And you can play with the geometry in the same way here, but on a kind of a higher level. Here we have sections with different leakage requirement classes. Let's say for a class A, from 0 to 300 profile, we will have one type of geometry, and we can divide this in different leakage requirement classes and corresponding geometry that we have already made in the design module I showed earlier. So we can try to load the first one. So it's about it's a more rough pattern. We see the drill holes loaded here in the model. And this is the input to the model. It's the output from the last model where we input here in the discipline model. And we can include another geometry with a bit more denser pattern. And the last one is for a very high leakage requirement. So we'll have a bit closer look on that one and see all the drill holes, the geometry drill, the grouting drill holes. And you see down here that the green ones are a bit more dense, a little bit more drill holes here. So it's a visual to see that this could be a good model or a planning model for this tunnel. Down here we have some with a low overburden, and we include some barrier holes in this planning model, the planning discipline model. So you can kind of play with the geometry in the same way, but on a higher level. based on the design of single models. And lastly, we can export quantities for just this geometry very quickly, just to hit the button, and then we have an Excel spreadsheet with the quantities that we have dynamically here. And this, if you change the geometry, this will also change. So it's quickly to inspect all these values. Okay, that was for grouting, and then we will have a look at how this can be done for rock bolting. I'm not going to detail here, it's much of the same principles, but the basis for this discipline or plan model for rock bolting is surface mapping. And we typically map the geology in different classes, for instance, using the Q system. And we can have a bolting pattern or different support classes with different length between bolts, and also shotcrete and different systems for different rock mass classes. So in this discipline model for rock bolting, we input sections with different Q values. For instance, from 4 to 500 profile number, we have a Q value of 3. So this is a sheet that is input to the model. We also have a distance between bolts, so the different support classes we have coded here. And this will be the input for the dynamically version of the model. And we have the center line for the tunnel again. And we'll connect this in the same manner to the script. And we have the same profile, we choose the profile. And you have bolt lengths down here for the quantity report. So we connect the center line again to the script, and we see the geometry is loaded directly. So we read in all these Excel spreadsheets. Here we can see different bolting patterns, and of course this is in the planning phase. So it will be adjusted on the phase. Also some profile numbers added to the right here. But it makes it easy to quickly adapt the design. So we can export all bolting locations. So this will be kind of theoretical here now, but it could be updated in the operation phase. We can also have a quantity report, like here, for the different bolts. Okay, yeah, so that was about it. It was rock bolting and geometry for rock routing. And over to you, Jessica.
Thank you, Tom. I will mainly talk about two things in my presentation. I'll start with how we can apply remote sensing technique to obtain a 3D rock slope model, and then to how to make use of this 3D rock slope model in bolting design, systematic bolting design. Remote sensing has been more commonly applied in acquisition of structural geology data. As you can see in the pictures here, to the left is a natural hillside, which is over 600 meters tall and over 500 meters long. And if we can put a LiDAR scanner on the opposite side of the hillside, or even fly a helicopter or drone, then we can have a model of the whole outcrop. To the right is a rock cut slope along a BC road. It would be very hard to go there to do field mapping because there's traffic and it can be dangerous. So we can also take pictures of the whole hillside, or if possible, to fly drones when there's no traffic to get an overview of it. With 3D models of rock slopes, we can get a better overview of the whole outcrop. We can get information on top or from the sides, and we can use it for analyzing the data in the office. We can make use of it to obtain discontinuity data. And in amount that it would be not possible to obtain it in the field manually in a short time. We can make use of this huge number of data to get a better statistic. For example, we can obtain the joint spacing between each joint set. And with a high-resolution model, we can also obtain a more representative joint roughness of sliding planes or joint surfaces. We can also get a more accurate estimation of the geometry, and we can use this geometry in an optimization of the rock support design or evaluation of the stability. We can also use it to estimate volume of potentially unstable blocks, which give us a better idea on how much bolting capacity that is required. This is an example we did for a forensic investigation of a rockfall failure recently in Norway. We made 2 photogrammetric models, one before the failure and one after the failure, and then we compare the differences of volume to find out how much rock mass has been fallen out of the slope, and we have a better idea of the geometry of the sliding plane. There are 2 major techniques that are mainly used in obtaining 3D models of rock slopes in geosciences. One is photogrammetry and the other is LiDAR scanning. We can use either of this to get 3D models, depends on the project size and locations and the environment. We can also use both to supplement each other. For example, one can use a LiDAR model to georeference the photogrammetry model that makes use of the high accuracy of the positioning from the LiDAR model, but also full color from the photogrammetry model. Here shows how one can obtain data from LiDAR and photogrammetry to obtain a 3D point cloud or later on meshes. You can see that by using LiDAR scanning, there's less processing procedure compared to using photogrammetry technique. Using LiDAR, you scan the surface, you get the already georeferenced point cloud because there's usually GPS inbuilt in the LiDAR scanner. Then you just have to read the data and then you get the 3D point cloud you want. But using photogrammetry, you have to think about the overlap between the pictures. And when you read it into your computer system, it runs and then find the common objects between each photos. And later on, you have to georeference the whole model. So the processing time for photogrammetry is longer than LiDAR and more complicated. The imaging technique or photogrammetric technique that's used that I'm talking about here, we call it structure for motion. Actually, you don't have to move on the go while you're taking pictures, but the sense is that you take pictures from different positions of the same object. And this kind of principle is the same as in human eyes, that you have a motion parallax where you can have a 3D representation of an object when you see an object from different positions. So by taking pictures from different positions of the same object and later on find a common object point between each image, and using this structure for motion algorithm, one can generate a 3D representation of the object. And it's commonly, sometimes people may confuse with panoramic pictures. To the left, this is how you take panoramic pictures. You take pictures from one point and then on the same objects parallelly. But if you go along the wall or go around the object or the point, then you can have a 3D representation using structure for motion technique. Based on experiences, to have an optimal overlap of the pictures, you'll get an accurate model, and that will have an optimum time of processing of the data. based on experience, about 80% of overlap along the flight line and about 60% across the flight line would be the best. And of course, if you take more pictures, you can get a more accurate model, but then the time of processing will be larger. To compare between photogrammetry and LiDAR, we find it there are advantages of using photogrammetry in when we are mapping rock slopes, rock mass, because you can try to trace along linear features that are not necessarily planes. By using LiDAR data, you scan the surface and then get the return. But if it's only a crack in the rock, you may not necessarily find it. And using photogrammetry, you can usually, for example, use unmanned aerial vehicles, drones, or helicopter, and again, you can fly around outcrop. And then you can have a better coverage and minimize blind zones instead of traditionally using terrestrial LiDAR. But you can also compensate this using a LiDAR on the drone. Photogrammetry products has a lower investment cost than the LiDAR scanner. But there are also some limitations using photogrammetry. First of all, the objects must be illuminated. So it's a limitation when you have to do make a model, for example, underground or in the shade. Photogrammetry cannot get around canopy, whereas LiDAR can scan several signals, and then you can try to filter out the first return to get the terrain model. And as I presented before, it takes longer processing time or more complicated procedures in data processing by using photogrammetry. And even though remote sensing has been commonly used these days, but still we use traditional methods to design systematic bolt support or simply single bolting. This is showing you how we do. We have a model and then we get a quite good idea and accurate geometry by drawing cross sections along every meter, for example. And then we find a typical cross section of the slope, put it into a program or to calculate by hand calculation the necessary support capacity. And then maybe we put it in a picture, send it to the client or the contractor. But sometimes there could be information flow error, or maybe the contractor does not understand your drawing. And in this mistake, it can be a rock slope failure, and it could cause a lot of trouble. So by using a parametric model design and use a CAD software like Rhino software, you can have a more visual and more realistic model that you can optimize your design, where you can see your design immediately and you can adjust the design in an interactive way. As Tom showed, here you can, for example, adjust the spacing or the angle of the bolt, and you can see immediately the results. And it can enhance the information flow if you can manage to export the geometry of the bolt to BIM. Then you can send it to the contractor and then they can make use of it immediately. And we can minimize the error in case people don't understand each other. Here's an example of how the idea of using Rhino Grasshopper in parametric design of systematic rock bolting. First, you define where you want to put the rock support. Next, you define where the potential sliding plane is. And then by generating surfaces from the point cloud using these two alignments, you get the necessary data for designing systematic bolting. These are the necessary things that you need. The white grid surface here is the real rock surface extracted from the point cloud. The yellow one here is best fit sliding plane you define, and also the purple here is the best fit surface of the rock slope. And we develop a script that have a simple function of how you can define spacing vertically and horizontally of bolts. You can also set clearance where if you don't want bolts on the edge of the surface, and then immediately you will get the bolts information, for example, coordinates, number of bolts, the length of each bolt, and also the orientation. Here shows how we want to apply parametric design based on the real geometry in designing rod support. As you can see, the yellow here is the sliding plane. And then you can define how much embedded depth you want your bolts to have. Here you can adjust the minimum embedded depth, then the results will be updated. And then you can have a better idea of how actually your bolts are embedded to a good rock. And there are many things that we can use Grasshopper plugins in Rhino. And there are more possibilities in terms of how you can make use of the program. The example that I presented here is a very simple starting release of the script that we made. And in the future, we'll add more complicated functions and more useful functions that can help with our everyday designing procedures. For example, one can use scripts or Python scripts in Grasshopper to calculate the necessary bolting support based on real geometry. Here is some extracts from master students that we supervised this year. His name is Olaf Rose at NTNU in Norway. He managed to write scripts that can define a block using joint planes, and then to extract the geometry, and then to calculate the stability of the block without bolting, and how a 50 kilonewton pretension bolt can help stabilize it. And also you can define your script so that the geometry of the bolt will fit to standards. And this will help engineers to easily produce design, and that can ensure that the design will comply with the standards. The next procedure is to enhance the workflow, information flow between design and also the BIM, and make it easier for production. We are developing a procedure on how to use Rhino Grasshopper to export design to BIM, where each of the objects will carry metadata that tell you about, for example, the bolting diameter, the bolting length, and also material. And then you can make use of these data to get the price and also maybe time for construction very easily. And it's a very useful tool that you can use in projects to estimate the time and cost that you need. So we see a lot of possibility in using the software. And that's the end of my presentation. If you have any questions, so just post it in the chat and we will answer it later. Thank you. And I will pass it back to Magnus.
That was all for this time. I hope you have enjoyed it. If you want to contact any of us you can see the email addresses here. And as I said in the beginning, answers to questions we will posted on the landing page. We're planning for holding a next webinar late September or early October. We have not set the final date yet, so please follow us in social media, and then more information will come there when the date is decided. We have not decided fully about the agenda the next time, but it will probably consist of both environmental 3D modeling and also how to combine Python, Rhino, and Grasshopper for making as-built models. But again, follow us in social media, and then more information will come there. Thank you all for joining us today. I hope you enjoyed the webinar, and I wish you all a nice evening, morning, or night, all depending on where in the world you are. Goodbye.